So in this final lesson of the chapter 2 or unit 2 here, what we're going to be taking a look at is basically some properties and some things that we can do with the dot product. Okay, so first of all, one of the things we're going to take a look at is now that we have the cross product, okay, we can now show that three vectors are coplanar in a lot more efficient method than we did before. What we did before was we had to come up with a, a a linear combination of two vectors to get to the third. And you see, if you remember when we were doing this, it was a very long process, right? We assumed that there was this linear combination. We had to show in between two of the equations, show for the third that it works, or it doesn't work, right? And then at the end, we figured out that whether or not they were on the same plane. Well, now that we have the cross product, what we're going to be using is this thing called the scalar triple, okay? Now, it's the scalar triple because we've got three vectors, okay? 1, 2, 3, so there's your triple, and it turns out to be a scalar quantity, okay? So all of this will be some sort of scalar quantity, all right, at the end. Now, here's the idea. First of all, let's take a look at what it means to have the vector here. Okay, number one, we do the vector first because a scalar times a vector crossed with a vector is a vector. All right, and then we know that u dot some vector, well, I'm just going to call it something else here. Let's say it's t, is true. It works. We can do that. Okay, so we do that first. Then we do the dot product, okay? We cannot do the dot product first, all right, because the expression itself will not make any sense. The reason why is because the dot product is a scalar, and we do not have a cross product between a scalar and a vector, right? Only between two vectors, all right? Now, the reason why this works to show that three vectors are coplanar or not coplanar, all right, is that when we take any two of the vectors and we cross them, we are going to get a perpendicular vector, okay? It's perpendicular to the two vectors in question, all right? Since it's perpendicular to the two in question, all right, if we then look at the third vector and dot it, if the third vector is then coplanar, all right, with the other two, then the cross product of the other two is going to be perpendicular to it, and you're going to end up with an answer of 0. Now, that's all fine and dandy talking about it, but let's see what it means, okay? So let's say what we have is we have a vector A, all right, we'll call that vector A, and we have another vector. We'll just say that that's vector B, okay? Those are on this plane, all right? We know that to be true. It's on the plane because we're saying it is, okay? Any two vectors define a plane, all right, that are non-collinear. So the cross between them, all right, this is A cross B. We know that A cross B is perpendicular to both A and B, right? Because it's perpendicular to the whole plane. So if we have a third vector that is on the plane itself, let's call this third vector C, then A cross B is perpendicular to C, okay? Since A cross B is perpendicular to C, when we dot C with A cross B, we know that the dot product is going to be 0, okay? That's the idea there, all right? That's if they're all coplanar. So that's coplanar. So hopefully that makes a little bit, it's a little clearer, okay? if, let's take this C off, and if the third vector is not coplanar, meaning it is outside of the plane, all right, it's going through the plane, in other words, all right, then we know that the dot product is not going to be 0 between the cross and C. So it's non-coplanar, okay? That's the idea. Those are the ideas behind this scalar triple, okay? So let's see if we can use it now. The notes themselves have another diagram you can take a look at, all right? Let's see if we can get or use the scalar triple, okay? So example 1, we're going to just set up any 3 vectors. We'll go 2, 3, 1. B is -4, 9, 2. And C we'll say is the vector 3, -1, -2. Okay? So using the scalar triple, we're going to see, are these coplanar? Are these coplanar? To show it again, we use the scalar triple. We can go A dot B cross C. All right. Now, A dot, the rest of it, we can't touch yet. Okay, so I'm just going to write the vector itself down like this, dot, and now do the cross product between B and C, right? Hopefully we've had a lot of practice with this. We can take a look at it and go, okay, so we've got -18 minus -2. Then we have 6 minus, no, minus 8. And finally, we have 4 minus 27. So hopefully you have this, okay? Make sure you're doing the work. You can always pause the video, do it yourself, and then find out what I've got at the end. And hopefully we have the same thing, and neither one of us made any mistakes. So -23. And when we go through this, I can already see this is going to be a negative number and not going to be 0, but we have -32 minus 6, -23. It's not 0, which implies they are not coplanar. Okay, that's the idea. They're not coplanar. All right. Let's go with examples that we know are coplanar. Okay, and see what happens. Let's show that we actually get a 0 in this case. So ones that are coplanar, we know that could be all on the major plane. Let's assume that they are all on the the YZ plane. So that means that X is 0 in all 3 cases. Okay, so that's what we're going to do. And we're going to show the scalar triple that it's going to end up being 0 as well. So we can say this is 1, 2. We could say -4, 7. And we can do 5, -3. Okay, we know they're all coplanar. We know the answer should be 0. Let's make sure that it works out to be 0. Okay, so the scalar triple, A dot B dot C, A 0, 1, 2, dot that with the cross product. So here's a cross product, right? -4 times -3 is 12 minus the 35. Jump over, looks like these end up being 0 and 0, right? If you do that quickly, if you look at it, okay, blocking out the middle term, we've got 7 times 0 minus 0 times -3. And then for the Z, we have 0 times 5 and then the 0 times -4. Okay. The dot product, well, 0 times anything is 0. And there, sorry, I'm doing it as a vector, which it isn't. It's all addition. And you have 0. Okay. So you're going to end up, therefore, they are coplanar. All right. So the scalar triple does work. All right. It does not tell us what the linear combination is. All right. That's when we have to go back into the long version to do it. But if we're just looking to see whether these are coplanar or not, the scalar triple works fantastic. Okay. That's what we want. It's very, very quick. Now, the other property, and there's a lot of algebra involved in this one. Okay. Is the cross product, does it have the distributive property over vector addition? Okay, so for any general three vectors, okay, does the distributive property hold true? Well, the quick answer is yes, you can see it here. All right, I'm not going to write it all out again, but I will describe each step along the way so that we can focus our attention on these. All right, so in the first step, all we did was we rewrote or wrote out what it meant to be b plus c. Okay, we're adding two vectors together, so we are adding the corresponding components. Okay, that's all it is there. In the next line, we had to carry out the cross product itself. All right, so we have the second, all right, we're looking at the A2 times the B3C3, okay, the B3CC, there it is there, minus A3 times the B2 plus C2, okay? That's the X component only. The Y and the Z work out the same way, all right? And you can go through that if you don't believe me, but it's the same way, all right? The idea, the properties come in, then what we're doing is we're taking these scalars and we're doing the distributive property on the scalars. We know they hold true, so we can perform it, right? So for the X component, we expand out, and that's what we end up with. Okay, the Y's, the Z's are the same way. That's just the algebra. Okay, it's like record keeping. Okay, or number tracking. Then from the next line down, all we're doing is we're taking the A's and B's terms and we're putting them side by side, right? The commutative property of scalars, we have that. The A and C's with the A's and C's. Okay, just look at the X component. The Y's and the Z's are identical. They're the same process. All right. What you can see that we're doing here is basically we're setting up the cross product between A and B, adding with the cross product of A's and C's, right? So that's what we have. We separated it. It's the addition of the two, and then we write it out at the very end, and we're all done. Okay? So go through that, take a look at it, all right? And make sure you understand how to go through kind of each step and why it works is because once we get inside of the components, they're scalars. The components themselves are scalars, so their properties hold true. All right. Now I do have another handout that's at the top of this page, okay, for you to take a look at. It's got a lot of the same properties as before. This is the handout itself. Describes what we have. It's kind of a general overview of the cross product itself, what it is geometrically, algebraically. All right. We have the scalar triple. We already know one of the properties that it doesn't have is the commutative law. So that's why we put a line through it. Does not hold true, right? It is not true. Okay. We just proved the distributive property over vector addition. All right. And finally, if a cross product produces the zero vector, then we know that the two original vectors are scalar multiples of each other. And this last paragraph here describes why. It's basically because the sign of zero or the sign of 180 degrees is 0, okay, at the end. So the magnitude is 0 and it basically has no specific direction. Okay, so that's what we have there. So you can take a look at those, work yourself through the questions that are here at the bottom of the page. All right, and good luck.